Yeah, I'm sitting right there. But there's an right next to this one? Yep.
Having trouble with the projector once again. So let me get that set up. Okay, this one is coming off.
They're both gone.
They're both, okay, cool. All right, so the first thing I'm going to do today, you probably have, for whatever reason, I always have trouble with my Unix operating system, so I will use Windows on this. The first thing I'm going to make an announcement is, you probably have seen that on Canvas. I made an announcement over there. So we have the 4 TAs ready to go. They finally got their office task assigned by the department. I asked all of them to be here today. So I'm going to introduce all of them to you. And here is a list of their office hours. They actually have started holding office hours this week. So if you have any questions regarding the class, regarding your homework, you should leverage this TA office hours as well as my office hours, which is mine is on Monday and Tuesday right before the lecture from 9:30 to 11. And these folks, we have 4 of them. Each of them will hold 2 sessions, and each session is for 2 hours. Okay. So why don't I go ahead and introduce them so that you know you can recognize their face. When you go talk to them, you know who you're talking to. Okay. Go down the list. The first TA is Rushani Nakamoto.
Yeah.
She is right here. Can you stand up, please? All right. All right. She is a master's student with us, and she was a TA for my grad level database class last semester and has done an excellent job. Her office hour is Tuesday and Wednesday. Tuesday from 10:30 to 12:30. Wednesday from 1:30 to 3:30. All of them are in the same TA office room, which is MEB 3115. They just have different desks. Okay, pay attention to the desk number. The next TA is Ray Dai. Ray is here. She is also a master's student. She worked with Roshni last semester as TA for my grad level database class. And also did an excellent job over there. And her office hour is Monday 3:30 to 5:30 and Tuesday 3 to 5 p.m. The next TA is Ji Yuan Li. He is a master student with us, and he did undergrad here, and he actually took this class with me when he was undergrad. And his office hour is Thursday from Thursday from 10 to 12, and Friday from 10 to 12 as well. Lastly, we have Jonathan Dunstan, and he is a master student. And I don't think you got undergrad here, no?
No.
No. Okay. His office hours are Monday from 1:30 to 3:30 and Thursday from 1:30 to 3:30. So we cover every single day. On some days, we even have 2 office hour sessions you can go to. So I believe this should, altogether should have provided comprehensive TA sessions for you to talk to, okay, to go to if you have any questions. All right, any questions regarding this? All right, if not, let's move on to the lecture today. What I plan to do today is to finish the discussion on relational model, as well as the discussion for converting your ER diagram to relational model. This is really important because some of you might have database experience before taking this class. And for those of you who do have some experience with database design and implementation, you always tend to consider your design, think about your design from a table point of view, right? Thinking about database is just a collection of tables without going through this ER design phase, and which is if you are really if you really know what you're doing, this is probably okay, right? Sometimes when I design a database application from scratch, I sometimes skip the ER phase because I can just kind of map the ER diagram in my brain and convert that to a relational model directly. But if you are new to this, or if you are not expert in database design, do not try to mix the table view with your ER design phase. Right? This will become clear once we finish the discussion on relational model and we talk about how to convert ER to tables. Okay. So let's go with this. So last time we talked about the basic setup for relational model. Relational model is nothing else but a collection of tables, and each table basically has 2 parts. One is what we call the schema part, which is those fields on top. And the schema basically consists of a set of columns, and each column has a name for the attribute from that column, as well as the type of that attribute. The type of the attribute basically specifies the domain of the attribute, the possible values the attribute may take. And then right below the schema of your table is the instance of your table. And the instance is nothing else but a set of rows. So the instance of a table . Hey, Jonathan, do you mind doing one thing? Can you go back to the office to grab some markers? Because I only have one. Do you know where it is in the copy room?
I don't think I have a key to that room.
Well, if you don't, ask the front desk. You have some?
Yeah.
Okay. All right, fine.
Okay. You got it?
Yeah.
Okay.
Remind me to bring some next time.
Yep.
All right, so instance of table is basically a set of rows. And these rows, sometimes we call them tuples or records. They refer to essentially the same thing, right? They refer to essentially the same thing. For example, in this case, the instance of this table is a set of 3 records, a set of 3 tuples, right? And mathematically speaking, okay? So towards the end of last lecture, I asked you this question, right? Do all values in each column of relation instance have to be distinct? So this actually is a somewhat tricky question to consider. So first of all, let's look at this definition. The instance of table is a set of rows. So mathematically speaking, a set should not have duplicate, right? whenever you see you claim it is a set, right? For example, this will be a set. That's a properly defined set, right? How about this one? Is this a set? Is this a set? No. So mathematically speaking, this is what we call a multiset. A multiset may allow duplicates, but a set itself does not allow duplicates. You cannot have duplicated values in a set, duplicated element in a set. So with that understanding, when we say an instance is a set of rows or tuples of records, that basically automatically implies those rows, tuples, or records must be distinct. They cannot be identical to each other. But we have to be careful in what we mean by having identical records. Okay? So for example, looking at this example, in this particular instance, it is possible for two records share the same name value. For example, I have two students who have, both of them are named as Smith. That's totally fine, right? So people have same names, that happens all the time. Some of them, they may have the same age value. That's okay. However, the important requirement is that you cannot have two records that have same values on all attributes. You must have at least one attribute, that two records will have different values on that attribute. In this particular example, that attribute will be SID, student ID. Intuitively, no two students can be assigned with the same student ID. Like all of you guys, each of you has a distinct, unique UID. Right? From the university point of view, they cannot assign two UIDs to two different students, because if that happens, there's no way you can distinguish those two students. Okay? So that's basically the basic requirement for a relational model. Next, I'm going to give you a quick overview of the language we're going to use to play with relational tables. This language is called SQL. SQL stands for SQL stands for Structured Query Language. And SQL is fundamentally different from, all the program languages you have interacted with before. The reason is, in SQL, you specify what you want, but not to worry about how to do it. So let me explain this a little bit. In any other typical programming language, like C or Java or Python or Ruby, whatever, you name it. A program, when you use your language to write a program, you basically need to do two things. One is, what exactly is this program supposed to do? What do you want this program to output? Okay, that is what you want. Not only you need to specify in your program what is this program supposed to do, but you also need, while coding this program, in the process of writing up your code, you are basically doing this part, which is specify how to get what you want. For example, a very fundamental operation people do in computer science is sorting. Right? You sort a set of elements. You do sorting. And that's basically what you want. You want, given a set of elements as input, you want to produce a sorted output of the same set of elements. That is what you want. But not only you need to specify what you want, which is sorting, you also need to specify how to do it, meaning using different sorting algorithms to do it. For example, the most naive algorithm is to do bubble sort. check the first element against all the subsequent elements. If it's bigger than any of the elements you have scanned through, you swap the position of these two elements. And you do that for the next element, so on and so forth. The complexity of that, obviously, is right? Because the first element you need to look at n elements, the second element you need to look at n minus 1 elements. You don't have to look at the element coming ahead of you because they guaranteed to be smaller than you. You only need to look at elements coming after you. So that's the complexity of this. So roughly this is to be precise, that's right. So this implies n squared complexity. So in this process, not only you specify what you want, but also how to do it, which is checking every element against element coming after it. You can also do sorting by, so this is one way of doing it. You can also do sorting by quick sort, right? You choose a pivot, a random element from your set, scan through all the elements, smaller ones go to the left, bigger ones go to the right. You do recursion. And each level, the cost is linear. You just scan this list, n elements. And how many levels of recursion you need to do? Log n levels. Because by log n levels, you reduce each sub-step into a single element, which is sorted already. Okay? So that gives you n log n complexity. So the reason I want to bring this up is to show you in traditional programming languages that you have dealt with, you need to specify what you want, and you need to specify how to do it. What you want is sorting, how to do it bubble sort or quick sort or merge sort, whatever. Right? You need to specify the algorithm of doing it. SQL, on the other hand, as we'll see in a minute, is a language where you only specify what you want, and you don't have to worry about how to do it. Sounds like magic, but that's actually a major strength for relational database management systems. That's exactly the reason why companies like Oracle can make billions of dollars, because they are really good at, doing this part, which is how to do it. Obviously, given a particular task, which is what you want, there are many different ways of executing that user requirement. And the tricky part, or the challenging part, is to figure out what's the best way, the most efficient way of doing it. Okay, and we will talk about that in the later part of this course, right? For now, let's look at give you a general overview of this language called SQL. And broadly speaking, we can partition by the functionality of this language into two parts. One is called data definition language, DDL. The other part is data manipulation language, DML. In today's lecture, we're going to mostly focus on DDL, because you're going to use that in your homework 1 to define tables and as such. Okay? So DDL, this partition includes those part of the SQL that is used for produce a new table, modify or update an existing table. And also it is used for specifying constraints and for security and access control purposes. And data manipulation language on this part, on the other hand, is used for specifying what you want, which is to construct a database query and to be executed by the database engine. Okay? So give you a quick overview of this language. So for example, if I want to create a new table, so by the way, on this particular slide, capital letters are what we call reserved keyword from that language, from SQL. So those in capital letters are reserved keywords from SQL. In practice, when you construct your own SQL statement, you don't have to use capital letters for those keywords. You can just use small case letters for those as well. The parser in a database system will be smart enough to figure out the reserved keyword regardless, whether you use small case or capital case letters. Here, I just want to highlight those reserved keywords to make it clear that these are system reserved keywords, and those small case letters are values you need to supply when constructing a SQL statement. Okay? So for example, in the first one, this tells you how to construct a new relational table in a relational database. you use the keyword create table followed by a name attribute, which is a value you're gonna specify. That basically specifies the name of the table. The naming convention is pretty flexible. You can pretty much use any choice that you like. The only constraint I believe most commercial databases will have is no space, no white space in a table name. No white space in a table name. And followed by a list of fields and their types. So field and domain, basically this is a set of attributes and their associated types for that given table. Essentially, what this tells you is to specify the schema for that table, the schema of that table. Okay? And then insert into, delete from, and update select. Each of these will do, for example, the insert into statement is for you to insert a new record into a table. And delete from is to delete a record from a table. And update is to update the value of an existing record in a table. Lastly, select is a DML language, which is to construct a database query to retrieve record from the table. I'm going to go over this using concrete examples rather than trying to explain this using their syntax. Okay? So we're going to go over this using some examples. So for example, let's look at create table first. By the way, you may wonder, we have so many different database vendors out there. You have Oracle, we have Microsoft SQL Server, we have MySQL, we have PostgreSQL, and so on and so forth. What happens if each of them are going to have different syntax in their SQL languages? Do I have to learn a specific SQL language for each of these database servers I'm going to interact with? The answer is no. The good news is you don't have to. The reason is for the benefit of this database industry as a whole, these database vendors a long time ago, like in late 80s or early 90s, they basically reached an agreement where each of these vendors, if you declare you're going to develop a relational database system as your product, you're going to sell that on the market, you need to conform to certain standard. And the query language is part of that standard agreement. Meaning that whether you are Oracle or SQL Server or MySQL or PostgreSQL, if you claim your system is a relational database system, then your query language must conform to this what we call SQL standard. Okay, so pretty much they share the same or similar syntax in these different database systems. Okay, of course, that said, the SQL standard only specifies the core functionality of this language. And each vendor may still extend this core set of features with additional database specific features specific to their product, to their implementation of relational database system. That means you may have additional syntax that you may have to learn for a particular database system, but it's very minimal compared to the core part of features that are common. Okay? So let's look at creating a relation in SQL. So this is an example of creating a table called student. All you do is create table followed by the name of the table. In this case, I name my table as students. And followed by a list of the fields in this table, which is the schema of the table. And each element in this list has two parts. One is the name of the field and the type of the field. Name of the field and type of the field. And char 20, char basically stands for character. So char 20 defines a character array of 20 characters. 20 characters. And each character we know is simply 1 byte. So char 20 also, you can view that as a byte array of 20 bytes. Byte array of 20 bytes. Basically, that gives you a string data type, up to 20 characters. Integer and float, those are very clear what they mean. The only difference, the only tricky part regarding data type in a database system is later on you will, I think I have an example of that. Later on you will see, in addition to char 20, you may also have something called varchar 20. Varchar 20. And this var stands for variable. Variable. It stands for this word. So to be more specific, what's the difference between the two? Okay, this variable here means variable length. To be specific, and this basically is interpreted as fixed length. Okay, fixed length. So what's the difference? When I declare char 20, what I tell the database system is that I want to declare a character array of 20 characters and with fixed length, meaning that each value from this field, every single value from this field must have 20 bytes, 20 characters, regardless the actual length of this value. Regardless the actual length of this value. For example, the name field is char 20, meaning that if you have a student whose name, just like my name, that's 6, 7, 9 characters, right? 9 characters. But when you store this value in this field, it will occupy 20 characters still. It will still occupy 20 characters, regardless of the actual length of this value. Does that make sense to you? What about a variable length char? Var char 20. Well, fixed length, variable length, right? Should be clear what it means. Let me ask the student to answer this. How about you?
So basically, it doesn't limit your name length to be 20. You can increase it and increase the space allocation for it.
Yep. What's your name?
Amit?
Ahmed. Ahmed's answer is it doesn't limit the length for storing a particular value. It will adjust the actual number of characters used for a particular value based on the length of that value. For example, in this case, if I store this as a bar char, then in the database system I will use exactly 9 characters to store this value rather than 20 characters. But then why you still need to specify a value 20 when declaring the type of this attribute? Well, that's to set an upper bound, upper limit on the values that go into this field. Question? Yeah.
So now we know what is the difference. However, why would I choose one over the other?
Excellent. What's your name?
Fahad.
Sorry?
Fahad.
Fahad. So that's exactly the next thing I'm going to discuss. The question was, now we know the difference, but then why we bother to have these two types? Why not we just go with one of them? And sounds like this is always a better choice. Okay? Adjust the number of characters used to store a value based on the actual length of that value. Why you need to, for example, if you use this to store this value, you are wasting 11 characters for storing this value. It only needs 9 characters, but you are using 20 characters. Why you want to do that? Well, this actually is not an easy question to answer because we need to understand the structure of the database system better in order to fully comprehend the subtle difference between the two. But let me try to give you a quick overview of the rhythm behind this. And later on, when we come to that part of this course, we will talk about this in further details. The point is, if you think about it, each database record, right, each student, suppose this is a single student record. Like in this case, student record. What I'm going to have is I'm going to have the first field, which is SID, name, login, age, and GPA. Okay? In a database system, this table will be stored on disk. Okay? This table will be stored on disk. And that's my first student record. And obviously, I won't have just a single student. I will have multiple student records. So after the first student record, it goes with your second student record, and so on and so forth. So you may have many student records. I say n student records. Does that make sense to you? Okay? So what's the benefit of using this? Well, the benefit is if every single field in a student record has fixed length, if every single field has fixed length, this whole student record has fixed length. Does that make sense to you? So for example, in this case, every single field in this schema has a fixed length. Regardless, the actual value goes to the first student record and the second student record and so on and so forth. I don't really care what are the values of the name for the first student, what's the name of the second student, and so on and so forth. Without even looking at those values, I know those student records will have same length in terms of storing them in my database. Does that make sense? So for example, if I assume integer 4 bytes, float 8 bytes, each student record will be 82 bytes. Will be 82 bytes. Okay? 20 plus 20 plus 10 plus 4 plus 8. Oh, sorry. 62 bytes. 62 bytes. So I know each student record will be 62 bytes, regardless of the values for a particular student. And this is important because if you think about it, this makes your database design implementation much, much simpler. Why? Because if I want to delete a student record, I can delete this student record, and this space emptied by this student record can be easily used by another student record, regardless the values for that student record.
So is it like sorry?
Yeah,
Is it possible to store a pointer to another variable that we can have like a string pointer or something?
So you're talking about how we're actually going to store the variable length record, which I'm going to come to that in a little bit. Let me finish the discussion right here, but you guys can appreciate the benefit of having fixed length records, right? So it's very easy for you to recycle the space used by a previously deleted student record. It's also very easy to make update. If I want to update the value of age or GPA or name, even the name of student field, I can easily do that without worrying about moving the other records to make space for the new value of the name attribute for a student. Now let's consider variable length. What's the problem with that? The variable length, the picture is different. So the first student may look like that, the second student record may look like this, and the third student record may look like this, and the fourth student record may look like this. Now immediately you see a problem, right? Which is if you delete this record, and later on you try to insert another student record, you may not be able to, most likely you won't be able to fit this student record into this space occupied by a previously deleted student record. And in order to reuse the space here, what you have to do, you have to move all of this student record forward by whatever the difference in terms of space of this record and this previously deleted student record. Obviously, that's expensive. Does it make sense to you? And same thing goes for update. Let's say I want to update the name value of this student. First of all, first time it's called Feifei Li. Okay? And then you rename this as Feifei. You only store the first name. So from 9 bytes, it goes to 6 bytes. So you have some space left over, which means you have 3 bytes. You have 3 bytes between the first record and the second record. If you want to use all the space available to you, you need to compact this record so that there are no empty space left in between 2 records. Which means you have to move all this record forward. Or in another way, if I want to, if this value becomes larger, then you, in order to store this value, you need to move all this record forward to make space for it. Okay? So this becomes really expensive. Now it goes back to his point, how you actually store a variable length record. And that is something I'm not ready to discuss today. And we will come to that point later on, but you are absolutely right. If you look at how database systems store a variable length record, they actually leverage the construction of pointers. They use pointers to keep track where each record locates at for variable length record. And more details, we will talk about that later on. I see your question over there. Go ahead.
Yeah, if if the characters are defined and confined to 1 byte each, how do you handle like Unicode data beyond just the single byte characters?
Yeah, so that's an excellent question. So, but in the short answer is, unless the database system you are using has a specific data type defined for you for that purpose, which is a single bit or whatever. Typically they call a bit map. Bit map is an array of bits. So each, the finest granularity that you can operate on is a single bit rather than a byte. If you have a data type like this available, obviously you can do operation on bit level, storage. Okay. Otherwise, either you define a customized data type in database system. Most database systems allow you to define a customized data type, where you define your bit level operation yourself, or you simply use a single character, just char 1, to store your value. Then you are wasting a few bits, but people may argue, why I care for a few bits. Does that make sense to you?
I think you might have misunderstood.
Okay,
I was
let's try to understand your question.
I'm worrying about like Unicode characters that are larger than 1 byte, not less than 1 byte, but larger than 1 byte, like Chinese. Or
The other way.
Yeah.
Okay. So first of all, most database systems, if you use PostgreSQL, MySQL, and Oracle, they do allow you to specify the default coding format for your database system. So you can specify, I'm using Unicode or whatever. Okay? And when you specify that, they will understand a particular character using that particular coding system. Like if you define your database system is using Unicode, so they will use Unicode to decode those characters. Does that make sense to you? For example, most database systems use UTF-8 as their default coding system. Does that make sense to you? And you can change this when you set up your database management system. You can change this default coding system when you set up your database system. And even if you set up your database system using UTF-8, later on you can switch to a different coding system. For example, if you talk about Chinese character, right? For example, my name, you try to write this. This is Li. This character, Chinese character, will occupy 2 bytes by default. And if your database system in order for your database system to properly decode this, you need to change your coding system. Rather than using UTF-8, you have to use some coding system that supports the understanding of Chinese character. Okay? So if you have further doubts, let's take this offline because I think that's not the core part to the understanding of this. But the basic point to your question is you need to pay attention to the default coding system in your database and change that accordingly if you are trying to deal with different character systems. Okay? Now, so that's the chart and bar chart discussion I would like to have. Now, you know how to create a table. Next, let's look at how to insert records into a table. Meaning that if you think about this, these statements allow you to define the schema of a table. But a table has 2 parts, right? Not only we need to worry about schema, we also need to worry about the instance of a table. How do we manipulate the instance of a table? Well, you use the insertion and the deletion statements. In order to add a new tuple or new record to a table, you do this. You do insert into, that's the system reserved keyword, followed by the name of your table, students, for example, followed by a list of the attributes that you want to specify values for. You want to specify the values for. Followed by the keyword values, and then a list of values which had a one-to-one correspondence between this list of values and the list of attributes you have specified earlier. Okay? Yes?
So does it have to be exhaustive, and if it is, does
No.
it use an NA?
The answer is no. Let me try to understand the question. There are 2 parts, I guess, to your question. One is,
Sorry, what was the question?
the question was, does this, I assume you mean the list of attributes, that this has to be exhaustive, meaning including all the attributes from your table. And then you talk about the non-value, which I believe is something else. Let me respond to the first question first. which is whether this list of attributes, that this has to be an exhaust list, including all the attributes from your table. The answer is no. That's exactly the reason why database system allow you to supply a list of the attributes when you insert a record. Otherwise, if it's always to be exhaustive, including all the attributes, you don't even have to supply this list of attributes because the schema of a table, once you define it, is fixed. Database knows the schema of your table. If you, by default, is going to supply values for all the attributes from a table, you don't even have to supply this list of attributes. You can just go ahead with insert into students, values, list of values. Does that make sense to you? Because the database system knows your schema. If you don't specify a list of attributes, I will assume that you're going to specify values for each single attribute for the schema of this table, and there's a one-to-one correspondence. So you only supply this list of attributes for two purposes. One is to make it more clear, even if you're specifying values for all attributes, you may still want to supply this list of attributes just to make your code easier to understand for others. Secondly, you don't have to supply values for all attributes. You can supply values for a subset of your attributes, or a subset of attributes from the schema of that table, For example, in this case, I can do insert into students, SID, name, and login. Then the first three values without the last two attributes. That's totally okay. I don't have to specify values for H and GPA. This brings up the second point he was trying to make. What about non-values? What about null values? Well, if you don't specify a value for a particular field, when you insert a new record, the default values for those fields will be null. Will be null values. There is, however, a constraint when you use this construction to insert a new record, which is the key attribute. We haven't talked about the key yet. We haven't talked about this concept yet, but for now, let's just think about this as the attribute that you use to distinguish every two records. For example, in this case, for student record, that key attribute is SID, because no two students are supposed to share the same SID values. Does that make sense to you? So that's your key attribute. The key attribute cannot be null. In other words, when you insert a new record into a database, you have to at least specify a value for the key attribute. A value for the key attribute. Okay? In some database systems, what happens is you never specify a key for your schema. You never specify a key for your schema. In those cases, the database system will automatically introduce a hidden attribute and that's typically called the ID of the record that has auto increment data type. There's a data type called auto increment. That's just an integer identifier. The database system manages that for you automatically. If you never specify a key attribute for your schema, then it will introduce a hidden attribute with the type auto increment. The first record will have value 1, the second record will have value 2, and so on and so forth, for that hidden attribute, which has an auto increment. Now you understand why it's called auto increment, because it automatically increases the value of this field for any new record coming into this table. Does that make sense? Otherwise, if you do have a key specified for your table, if you do specify a key for your table, in this case, SID is my key, then when you insert a new record, you need to specify at least the value for the key attribute. Okay? The other attributes is optional. It's up to you whether you want to specify a value for those or not. If you don't supply a value for those attributes, then those will be automatically set to null values. Question over there. So why don't you go first?
Is there a way to, I guess, make multiple key values for each row? Like, for instance, we would have SID and login potentially to both
Excellent.
be unique to
Yep.
each student.
That's an excellent observation. What's your name?
Parker.
Parker. Parker said, is it possible, let me repeat the question, is it possible to have multiple keys per schema? The answer is yes. The observation from this table, for example, obviously we know student ID is unique, but obviously login should be unique too. So I may have multiple key fields for a given schema. And we will talk about that in the next few slides.
Can we set the default to be something other than or no?
Yes, you can. That's something we will talk about that as well. You can, if you don't want to use null value for a particular field as a default value, you can always, at the time of creating your table, you can always specify a default value on any given column. And different columns may have different default values. Okay? So that's the insertion statement. And you have insertion, you must have deletion, right? So that's just the nature of the system. So we will have deletion statement like this. What you do is you do delete from, those are system reserved keywords, followed by the name of your table, the name of the table that you want to delete the record from. Let's ignore this S for now. Ignore this for now. And then you have a where clause. This is what we call the where clause. And the where clause is used to specify conditions that must be met in order for a database to execute the action you have specified. Okay? So the where clause is used to specify conditions that must be met in order for the preceding action to take place. In this case, the preceding action is delete the record. So in order to delete this record, this condition must be true. So this clause, where clause here, is essentially a Boolean expression that evaluates to either true or false. A Boolean expression has only two possible outcomes, right? Either true or false. So this is your where clause for this statement, and this is your Boolean expression, and this evaluates to either true or false. And the question is, on what values do you evaluate this Boolean expression on? What values do you evaluate this Boolean operation on? Well, you evaluate the Boolean operation over every single table, over every single record from the table you have specified in the from clause. This is what we call the from clause. So you evaluate this Boolean expression against every single record from the table in the from clause. So for the first record, you check this. For the second record, you check this. For the third record, you check this condition, one by one. And whenever this condition is true, evaluate to true, for that given record, the preceding action will take place. Meaning that if for the third record, the student name is Smith, that record will be deleted. If the fourth record, the name is not equal to Smith, this evaluate to false, nothing will happen. And you do this is kind of like a for loop. For each record, you do this, and when the condition is true, you delete the record. Does that make sense to you? Any questions regarding this? Now, let's understand this X. And this is what we call alias. Okay, alias. And for now, you can think about this just as what we call a renaming operation, right? Renaming operation. So I rename this student table as S. So you can think about this as a kind of like a symbolic link or a pointer to this instance. And in this particular case, the sole purpose of doing this is to make it easier to make a reference to an attribute from that table. Otherwise, think about if you want to refer to the name attribute from the student table, and to be 100% clear, suppose if you have another table here that also has a name attribute, and you want to be clear which name attribute you are referring to, you have to do students.name, which is, if you didn't do a good design job for the name of your table, you may have to write a really long word, so which is cumbersome, right? So for one purpose, this alias variable is to simplify the writing of your queries. But later on, I will show more examples where there are cases where you have to use this alias construction to make your query ambiguity-free. In this particular case, you don't even have to use this, right? For example, you can ignore this s and say students.name, or you can simply ignore s completely, even without supplying students here, because there's no ambiguity involved here. There's only one table in the front clause, and there's only one name field from that table. So there's no ambiguity whatsoever, so you can safely ignore this for now. But later on, I will show you examples where this is absolutely necessary. When you have multiple tables, they all share common attributes, then this renaming operator becomes critical for you to get rid of ambiguities. Okay? Now let's talk about keys. Okay? Let's talk about keys. So just now, I think Parker, I believe he mentioned the observation he made, which is for a given schema, you may have multiple attributes that are distinct, that are unique, right? What about those? Well, all of them are called keys. So let me give you the definition of keys first, then we'll go back to that example in the last slide. First of all, let's look at the definition of keys. We say a set of fields is a super key if no two distinct tuples can have same values in all key fields. So that's the definition of super key. So super key, if you look at this definition, it has two requirements. First of all, it's a set of fields, of course, from the same schema. Okay, from the same schema. So a schema may have multiple fields, right? Any subset of those fields can be a candidate for your super key. But that's only requirement number one. Requirement number two is no two tuples of course from the instance of that schema can have same values on all super key fields. The keyword is on all super key fields. Meaning that it's possible that two tuples may share same values on some attribute from a super key, but they cannot have same values on all super key fields. Okay? Let me give you an example. Let's use students as an example. Okay? Let's check. Is this a super key? First of all, this is a subset of fields from the student schema, so it can be potentially a super key. Does that make sense to you? Yes? So the condition one is met. It is a proper subset for the students. For example, this will not be a super key for students. For example, SID and address. This cannot be possibly a super key for the student schema. Why? Because it's not even a proper subset for the schema of students. You don't even have an address field in the schema of students. So it's not a proper subset of the student schema. But this one is. So I do satisfy the first condition, but you still need to satisfy the second condition, which is no two tuples, which means no two student records can have same values on all super key fields. Is it true or false in this case? Somebody say yes or no?
It's not.
Huh?
It's not true.
It is not true. Meaning?
So that SID itself is unique regardless of name.
Exactly. But with respect to this requirement, what you said is true, which is SID value is unique, which means no two student records will have same student ID values. They may have same student name values. They may not have the same name, but they may have the same name. But with respect to this requirement, is it true or false?
It's true because even if you have the same name
the tuple will be unique.
Yes, even if you have same name, by what you said just now, it's guaranteed that the student ID value will be different. So the two tuples are still going to be distinct. Okay, what's your name?
Raj.
Raj, what's your name?
Daniel.
Daniel, Raj and Daniel. So thanks for your discussion, make it clear, okay? So two tuples, like Daniel said, SID value must be distinct. And Raj then adds to that saying, yes, if you look at two tuples, the name value may be the same, but I guarantee you the SID value will be different. Because of that, the two tuples are still different. So it is a super key. It satisfies both conditions. Now let's look at another example. What about name and age? Is this a super key for this schema?
No.
I hear a lot of no, right? The answer is no. First of all, it does satisfy the first condition, which is it is a proper subset of this schema. However, if you look at two student records, it is possible that two student records are going to have the same name and same age. Does that make sense? It is definitely possible to have, in fact, we may have that in this classroom. The two of you have the same name and the same age. So this is not, this is not super key. Okay? So that's the definition of super key. So a trivial super key for any schema is what? Is the schema itself. A trivial super key for any schema is the schema itself. Why I make that claim? The reason is, first of all, a set is considered a proper subset of itself, right? So the schema is a proper subset of the schema itself. It is a subset of the schema itself. So requirement number one is automatically satisfied. The schema itself, it is a set of fields from that schema. Just have all the fields. And by the earlier discussion I mentioned, a fundamental requirement for relational model is that no two tuples can have the same values on all fields. Right? That's the default requirement for relational model, meaning that you cannot have duplicate records. And that's where I mentioned instance is a set of records, meaning no two records can have same values on all fields. Yeah, question over there?
Yes, so what you're saying is basically that, I think, is a trivial super key is just the full record.
Yes, exactly. Not the full record, the full,
Well, it'd be the full record because that would be every field.
well, if you see a full record, this is a record.
Yes.
But these are a set of values. A super key must be a set of fields, not a set of values.
Oh, I see. So just
So
the
this
content.
is your super key.
Yeah.
So it's not, that's not the record, that's a schema.
That's the
of-
value of the. Right.
Yes, when you talk about values and records, you are talking about an element from the instance of relation, which is from here. When I talk about schema, it refers to, strictly speaking, only this part.
Okay, thank you.
So you cannot see a record as a super key, but the schema is a super key. Okay? Next, let's talk about the concept of key. So now we understand super key, let's try to understand the concept of key. Okay? First of all, this is going to be recursively defined. So we're going to use super key to define key. First of all, it is a super key. It must be a super key. Which means this cannot be a key because it's not even a super key. This potentially is a key, but obviously we're going to have more constraints. Otherwise, what's the difference between key and super key? So this could be a key, but stay tuned. Let's look at the second constraint, which is the second constraint is a little bit trickier to understand, but let's try to understand this together. Right? No proper subset of this super key is a super key. Okay. No proper subset of this super key is a super key. Okay? It's rather contrived, right? It's like What does it mean? Okay, let's look at an example, try to understand this. Right? So SID and name, constraint 1, satisfied. It is a superkey. Constraint 2, let's look at the proper subset of this superkey. What are the proper subset of this superkey? Well, I'm going to have SID, that's a subset of this. Name is another subset of this. What else I may have? I may have empty set as a proper subset of that. That's it. Those are the 3 proper subset of this superkey. That make sense to you? And the requirement is none of them can be a superkey in order for this to be a key. Let's check this one by one. First of all, check the leader. This obviously empty set cannot be a superkey. It's not even a set of fields. So this is out, disqualified. What about this? Is this a superkey? Obviously no. It is a set of fields, which is a single element, but 2 records definitely can have same name. This is not a superkey. What about this guy? Well, you have trouble. Now this is a superkey. Now going back to this definition, because SID is a superkey, SID name cannot be a key. It is only a superkey, but not. By this definition. Okay? Does it make sense to you? So what is the key in this case? Well, if I look at SID, it is a superkey because it is a proper set of fields from the schema, and no 2 tuple can have same values on SID. So it is a superkey. Second constraint. What are the proper subset of SID? Well, it's only empty set. And that cannot be a superkey. So the second constraint is also met. So this becomes a key. This becomes a key. So now you see the significance of the significant difference between key and superkey. Roughly speaking, yeah, go ahead.
What do you mean by a proper subset?
Proper subset, that's the mathematical definition, right? So if you have learned discrete math, if a set has n elements, a set with n elements, the proper subset are those sets where you randomly choose n minus 1 elements, or randomly choose n minus 2 elements, all the way to randomly choose only a single element, or choose no element at all. So the number of proper subsets for a set with n elements is how many proper subsets you may have?
N minus 1 factor.
You have this many proper subsets for a set with n elements. N choose n minus 1, n choose n minus 2, until n choose 1, until 1, which is the empty set itself. What about subset of this n elements? The difference between subset and proper subset is that a subset for a set including the set itself, in addition to all these ones. A proper subset must be a set of elements that's smaller in size than the original set. So it doesn't include the set itself. Okay? What about if you have more than one key for a relation? It goes back to Harper's observation. We know SID is a key in this case. And obviously, for student table, there's another key for the student table, which is by the way, how do you compute n choose n minus 1? For example, in general, how do you compute n choose k?
factorial.
Okay? So by that argument, n choose k actually equals to n choose n minus k. It's the same thing. Okay? Now, coming back here, what about if you have more than one key for a schema? So what about login? First of all, it is a super key because it is a set of fields from that schema, which has a single field, which is login. And no two student records have same login value. That make sense? So it is a super key. So the first requirement is satisfied. The only proper subset of this super key is what? Is empty set itself, which is not a super key. So the second constraint is met as well. So it is a key. So this example, a simple example like student, shows you that you may have two keys. Key number 1 and key number 2. By the way, it is possible that you have keys, you have multiple keys of different lengths. In this case, I have two keys. Both of them have a single attribute. The first one has SID, the second one has login. However, it is definitely possible to have multiple keys of different lengths, different number of attributes. For example, if I tell you, that's a big if, okay? In general, it may not be true, but if I tell you, I need to assign a distinct GPA value for students for each age group, or for each student. Every single student, okay? Let me put this way. How do I? You may have the same GPA value. So in other words, the age and GPA combination must be distinct. In other words, no two students. Okay, here is the constraint. No two students of same age will have same GPA values. That's just a requirement of this particular university. Sounds, bizarre, but let's say that's, for the argument's sake, that's the requirement. In my university, if you have the same age, you must have different GPA values. If you have different age values, for example, one is 18 years old, one is 19 years old, then it's okay to have same GPA values. But if you are both 18 years old, you must have different GPA values. Does that make sense to you? Suppose I tell you that's the case. Well, then the age and GPA combination, this become a key. Because the combination is unique, no two records will have same age and GPA values, but every single one of them is not a super key. You may have students with same age, you may also have students with same GPA, but the combination of them is unique. So this is another key, in addition to SID and login. My point is, you may have keys, multiple keys of different lengths. And so you may have multiple keys, that's the bottom line. When that happens, you choose one of the keys as your primary key, and you choose you being the database administrator. When you design this database, you have the choice of specifying which key is my primary key. You choose one of the keys as your primary key. The other keys, the ones you didn't choose as primary key, the other keys automatically become what we call the candidate keys. You understand? Okay? It's like election year, right? You have presidential candidates. Only one of them going to be your president, right? At least the Constitution says so far, we do not allow two presidents, right? So one of them will be your primary key. Your primary key is your president. The candidate keys are, unfortunately, the losers, right? Those presidential candidates, but who do not win in the end. Okay? So those are your candidates. Okay? So how do you specify candidate key and primary key in create table statement? Very simple. You do your create table statement. In the end, you specify the keyword primary key followed by the set of fields that form your key. This could be a set of fields or a single field, depending on what is that key you are trying to define, right, as your primary. So in this case, for example, in the enroll table, which tells you which student enroll in which class, an obvious primary key is what? Is a combination of student ID and course ID. So if I tell you that's your primary key, what that means? That means, actually, this is the university that you probably don't want to go to, right? What that means? That means this is the university where you cannot fail a class. If you fail, you cannot take the class, the same class again. Because student ID and candidate and course ID is a key, right? So the same student ID and course ID combination cannot appear twice, which means, and the student, you cannot take the same class twice, which means you cannot fail. Does that make sense to you?
I've got a question.
Yeah.
So let's say you have an entity that the only key for the entity is the set of all fields in the.
It is possible, yes.
So is it considered is it okay, because that gets messy when you're trying to use that as a foreign key and you have to copy all those fields into the new relationship. Is it okay to create just another field that's an ID? And
Totally, yes. Daniel's question, let me repeat Daniel's question was, it is possible to have a scenario where the only key you have is the schema itself. It is definitely possible. In that case, it is inconvenient for you. We haven't talked about foreign key, which I'm going to talk about in a minute. It's inconvenient for you to use that as a key because other table may refer back to this table using this key as what we call a foreign key, which I will explain in a minute. It becomes very cumbersome to do that. In that case, can I introduce another field, which is the sole purpose of this additional field is to serve as a unique identifier, and then that becomes my key? The answer is yes. And that goes back to what I have erased now. Even if you don't do that, sometimes database system will automatically do that for you, which is to assign a hidden attribute called ID, or whatever they call it, that has auto-increment data type. So, yeah, go ahead.
But can you do like where queries on that auto implement?
Depending on, that's a good question, but it really depends on the particular database system that you are using. Some database system will make that a hidden attribute, meaning that it's used for internal system kernel purposes to distinguish records, but it's not exposed to the users of the database. In that case, you cannot query on that attribute. Some database system will make it explicitly attribute automatically, so you can actually see the attribute. I saw another question over there, Rush.
So doesn't it make sense to just make one column or what field a primary key and then always have like, because isn't it always messy to have more than one field as a...
Well, not necessarily the case, right? For example, I'll give you a simple example where I may have, let's say I have an animal database, right? A set of animals. And each of them has a name, has an age, has a type of animal. And that's it. But those fields, if you think about it, none of them can be used as identifiers. So you have to introduce an artificial attribute, which is called animal ID. And this is only used by the database to distinguish animal records. For animals themselves, they don't care what is my ID. Right? For human beings, in US, you care what's your social security number. That's an identifier. But for animals, obviously, I'm not aware we have social security number for animals yet. Right? But who knows? Maybe one day you have to pay tax for social security attached to animals too. It may happen. All right. Well, you can make an argument that's for the general well-being of the society. The animal is part of our society. Right? So things can happen. All right. So what about the design down below? What does this mean? So in this case, if I tell you that I have this constraint, which is students can take only one course, and receive a single grade for that course. Further, no two students in a course receive the same grade. If I tell you this constraint, what are the keys for your design? What are the keys for your schema? First of all, student can take only one course. That means in the enroll table, student ID is good enough as a key because you can only take one course. So the same student ID value is going to appear a single time. If a student ID value is going to appear, it's going to appear only a single time, which means it will be a key. It will be a key. So I can use that as my primary key. So that's my primary key. Now let's look at additional constraint. No two students in a course receive the same grade. That tells you the combination of course ID and the grade must be unique. Because if you're in the same course, which means CID is the same, the grade value must be different. So this combination must be unique by this constraint over there. So that's another key. I can use that as my candidate key. And the way you specify candidate key is to use the keyword called unique. You can flip this around by saying this is my primary key and this is my candidate key. And all you do is primary key and unique. Then you're done. With this example, one thing you notice, which is the candidate key and the primary keys, where do they come from? Where do all your keys come from?
Specified constraint.
Yes, they come from the specified constraint from your user requirement document. You don't make up those keys by yourself as database administrator. You decide what are the keys based on and solely based on user requirement. A single statement in your user requirement totally change who can be keys for your schema, as we demonstrate here. Okay. Lastly, I'm going to talk about foreign keys. A foreign key is a field whose values are keys in another relation. So now let's look at this setup. Students table, I have enroll table. So the key for my student table is student ID. But I also use student ID in the enroll table to indicate which student has taken which class. So that student ID field in the enroll table is what we call a foreign key because it is a key in another table. And foreign key, the purpose of foreign key is to link records across multiple tables. So you can kind of think about foreign keys as pointers to another table. So these lines are imaginary, right? They do not exist in your database, but you can imagine the foreign keys are kind of like serving as a pointer referencing back records in another table. And the way you specify foreign key is very simple. After your primary key, for example, the enroll table, the primary key is SID course ID. For example, that's the case, which tells you a student may take multiple courses, but a student can only take the same course once. If you're using SID, CID as your primary key, what that tells you is a student may take multiple courses. That's why student ID value itself cannot be a key. But if you do take multiple courses, you can take the same course only once. So the combination of SID, CID is unique. So that's your primary key. And in this example, SID is a foreign key. And the way you specify that is you create a table, you specify your primary key, and last thing you specify is what we call foreign key. You specify the keyword foreign key with the field, that's your foreign key, which is SID in this case, and use the keyword references followed by the table name where this is a key. Okay? Before I let you go, one announcement. I didn't manage to cover the part I would like to cover, which is to convert ER diagram to tables. As a result of that, because we lost the lecture on Monday, so I'm not able to cover that before next Monday, which is the homework is due. But homework requires this part. So for that reason, we're going to have an extension on your homework. The homework will be due on Wednesday instead of Monday. And we will talk about how to convert ER to tables on Monday's lecture. One last thing before I let you go is really, really important. When you do your design for your homework 1, when you are working on the ER diagrams, do not, Let me capitalize this. When you are in the design phase, in your ER diagram, do not think about tables. Do not view them as tables. Do not even think about tables. Focus on your ER design. And then by Monday's lecture, I will show you how we can systematically convert your ER design to tables. If you start mixing these two things together, table and ER diagram, you will come out with bad design oftentimes. Okay? Or separate them. Don't think about them together.
Oh yeah. Only from 3500. Yes. In the second part, programming, right? Of the side. Are we programming anything or?